In this video, we will discuss the stereochemistry for an SN1 reaction. As we're doing that, we will compare it with the stereochemistry for an SN2 reaction. We discussed SN2 stereochemistry in the SN2 series, so we might as well briefly review that. Do you remember what's the key fact about SN2 stereochemistry? The key fact is that the product of an SN2 reaction will have inversion of configuration at the alpha carbon. Here's a better way to put that. If the alpha carbon is a stereocenter, then SN2 will give us an inversion of configuration at the alpha carbon. Do you remember why? Do you remember why this is? Here's the answer. In the SN2 series, we learned that when a nucleophile attacks an atom that's attached to a leaving group, the nucleophile attacks from the side opposite to the leaving group, and that opposite side attack results in an inversion of configuration at the alpha carbon. I hope that was a review for you. Now let's compare that with the stereochemistry for an SN1 reaction. Well, let me ask you, is this idea going to be relevant for SN1? Will this idea be relevant for SN1? Pause and think about that. I hope you said that this was not relevant because in an SN1, when the nucleophile attacks, the leaving group is no longer attached to the alpha carbon. Here's one of our previous SN1 examples. Now notice that in SN1, the leaving group leaves before the nucleophile attacks. And when the nucleophile attacks, the leaving group is no longer attached to the alpha carbon. When the nucleophile attacks in an SN1, the leaving group is already gone. Therefore, this rule is not applied. The nucleophile is not attacking an atom that is attached to a leaving group anymore. So this rule is not going to apply for SN1. So how do we decide from what direction the nucleophile will attack this alpha carbon? So the important thing here is that the nucleophile is attacking this positive carbon. Positive carbons play a very important role in organic chemistry. So there's a special name for a positive carbon. Do you know what the special name is for a positive carbon? A carbon with a positive formal charge is called a carbocation. A carbocation. Do you understand why that's a logical term? Why is it called carbo? Because it's a carbon, carbo for carbon. And do you know what the term cation means? Do you know what a cation is? Did you know that cation means a positive ion, and anion means a negative ion? So this is called a carbocation, cation because it's a positive ion. How can you remember the difference between cations and negative ions? Well, a good way to remember it is you could imagine that the N here stands for negative. If you think that N stands for negative, then you could read this as a negative ion. And anion is a negative ion. And then another trick we can pull here is we could say that the T in cation looks like a plus. The T in cation looks like a plus, so then this looks like a plus, a positive ion. A positive ion because the T looks like a plus. A negative ion because the N stands for negative. That's how you can remember the difference between cation and anion. All right, so this is called a cation because it's a positive ion and carbo because it's a carbon. Is this a carbocation? No. This is a cation because it's positive, but it's not a carbocation because it's not a carbon. So a carbocation is a carbon with a positive formal charge, not just any old atom with a positive formal charge. This is a cation, but it's not a carbocation. I want to define that carefully because carbocations play a crucial role in the entire remainder of your Ochem class. So we need to be very clear about them. So now we've learned what a carbocation is. All right, so what do you need to know about carbocations? Well, you need to understand the geometry of a carbocation. Do you remember the different types of geometry in organic chemistry? The two key geometries that play the most role in organic chemistry are tetrahedral and trigonal planar. Tetrahedral and trigonal planar. So can you figure out which of these carbons are tetrahedral and which are trigonal planar? Well, here are some rules. When a carbon has 4 attached atoms and no lone pairs, it's tetrahedral. When a carbon has 3 attached atoms and no lone pairs, it's trigonal planar. So I hope it's clear that all of these carbons are tetrahedral. All of the carbons in this picture are tetrahedral. They all have 4 attached atoms and no lone pairs. For example, carbon 1 here is attached to carbon 2 and 3 hidden hydrogens. 4 attached atoms and no lone pairs. All of these carbons are tetrahedral. But notice that a carbocation has, whoops, this meant to be 3. A carbocation has 3 attached atoms and no lone pairs. Carbon 2 in this picture has 4 attached atoms. After it turns into a carbocation, it has only 3 attached atoms and no lone pairs. So carbocations have trigonal planar geometry. It's very important to memorize that carbocations have trigonal planar geometry. What's the geometry at a carbocation? Trigonal planar. That's important to have memorized. So in this picture, carbon 1 is still tetrahedral. Carbons 4 and 3 are still tetrahedral, but in this picture, carbon 2 is trigonal planar. So in this picture, carbon 2 begins as tetrahedral, but then in this picture, carbon 2 changes to trigonal planar. And then in the final product, carbon 2 has changed back to tetrahedral. In this picture, carbon 2 has changed back to a tetrahedral geometry. We didn't actually draw that geometry when we did this problem. We didn't draw a tetrahedral geometry because this is not a stereocenter. We don't really care about the geometry when something is not a stereocenter, so you don't have to draw it accurately. So we didn't try to draw the tetrahedral geometry accurately here because carbon 2 was not a stereocenter. But when something is a stereocenter, it's important to draw the geometry accurately, and we'll show how to do that soon in this video. Before we proceed, let me make one other comment about a carbocation. It's good to know that carbocations have incomplete octets. It's good to know that a carbocation has an incomplete octet. That should be obvious because it has 3 attached atoms and no lone pairs. That gives it only 6 surrounding electrons. That's an incomplete octet. We've really been taking that for granted when we do this step. Here we're showing the nucleophile forming a new bond to the carbocation. How did we know that the carbocation was going to have room for the new bond to the bromine? Because the carbocation has an incomplete octet. The reason the nucleophile is able to form a new bond to the carbocation is because the carbocation has room for a new bond because it has an incomplete octet. Okay, that's not directly related to geometry, it's just a useful fact I thought that I would mention. Please pause the video and try this exercise. Now we'll discuss. First, we have to identify the correct geometry. Well, carbon 2 is a neutral carbon, so it should have 4 bonds. The 2 bonds we can see and 2 hidden hydrogens. So this would be a carbon with 4 attached atoms, carbon 1, carbon 3, and 2 hidden hydrogens. It has no lone pairs because the 4 bonds are already an octet, so we identify that carbon 2 has tetrahedral geometry. But our goal here is not just to name the geometry, but draw the geometry. So to draw the correct geometry, we have to show all the atoms attached to carbon 2. So we should also show those 2 hidden hydrogens. So here's the wrong way to do that. We can't just put them on solid bonds. We can't just put them on solid bonds because that would not be a tetrahedral geometry. That would be a flat geometry, not a tetrahedral geometry. Solid bonds would show that all the bonds were in the plane of the page. So to show that this is tetrahedral, instead we have to put one of the hydrogens on a wedge and one on a dash. That's a correct drawing of tetrahedral geometry. To draw tetrahedral geometry, we can draw 2 of the attached atoms in the plane of the page. One of the attached atoms in front of the page on a wedge, and one of the attached atoms behind the page on a dash. That's a correct way to draw tetrahedral geometry. There are other possible ways to draw tetrahedral geometry, but this is by far the most common. 2 solid lines, a wedge, and a dash. The most common correct way to draw tetrahedral geometry is 2 solid lines, a wedge, and a dash. it would certainly be a mistake to use 4 solid lines. So why did we use 4 solid lines in this picture? Because since this carbon is not a stereocenter, we didn't care about showing the correct geometry. When a carbon is not a stereocenter, oftentimes we don't care about showing the correct geometry. So this picture does not correctly show the geometry around carbon 2, but we don't care because since carbon 2 is not a stereocenter, the geometry of carbon 2 was not interesting to us. Of course, this carbon 2 is not a stereocenter either. This carbon 2 is not a stereocenter either, but in this case we did care about showing the correct geometry simply because the problem was asking about that. We cared about the correct geometry for this problem, even though carbon 2 is not a stereocenter, simply because the question was asking about that geometry. So the correct way to draw geometry for a tetrahedral carbon, one correct way, is 2 solid lines, a wedge, and a dash. But when a carbon is not a stereocenter, oftentimes we don't bother to draw the geometry correctly. Please pause the video and try this problem. Now, carbon 5 is a carbocation, and we've learned that that is trigonal planar geometry. We want to show all the attached atoms. Well, what the other attached atom here is one hidden hydrogen. Remember, a carbocation has 3 attached atoms, an incomplete octet. A carbocation with an incomplete octet has 3 attached atoms. So there's one hidden hydrogen here. Now the key thing is we're not going to draw the hidden hydrogen on a wedge or a dash. If you draw that hidden hydrogen on a wedge or a dash, that would be a mistake. Remember, planar means flat, all in the same flat plane. So that the hydrogen should be in the same flat plane of the page as carbons 4 and 6. The correct way to show this geometry is all 3 attached atoms on solid lines to show that they're all in the same plane of the page. If you drew this hydrogen on a wedge or a dash, that would be an incorrect way to show the geometry for a trigonal planar carbon. The correct way to show trigonal planar geometry is 3 solid lines. There are other correct ways to show trigonal planar geometry, but this is the most common, so this is the one that we're illustrating here. Okay, so you make sure that you have memorized the correct way to show tetrahedral geometry, 2 solid lines, a wedge, and a dash, and the correct way to show trigonal planar geometry, 3 solid lines. 3 solid lines should make sense. By using 3 solid lines, we show that all of these bonds are in the same plane. They're all in the plane of the page. That's what drawing a bond as a solid line means. Notice that tetrahedral geometry is not planar. These bonds are not all in the plane of the page. The bonds to carbon 1 and 3 are in the plane of the page, but the bond to the hydrogen points in front of the page, and the bond to this hydrogen points behind the page. So a tetrahedral geometry is not planar. And we show that by showing 2 of the bonds on a wedge and a dash. Now, how can we use this geometry to figure out SN1 stereochemistry? Well, we said that a carbocation has trigonal planar geometry. It's called trigonal, partly because it's attached to 3 things. Trigonal attached to 3 things. And planar, what does planar mean? Planar means flat, in a flat plane. The key thing to understand about trigonal planar geometry is that it is flat. The 3 things around the carbocation are arranged in a flat plane. In trigonal planar geometry, the 3 things that are attached to the carbocation will be arranged in a flat plane. And we'll see why that's important. Now we can come up with some rules that will help us with SN1 stereochemistry. Here's the rule. When a nucleophile attacks an atom that has trigonal planar geometry, the nucleophile can attack from either of the 2 directions that are perpendicular to the flat plane. Let's make that a little bit more explicit. When a nucleophile attacks an atom with trigonal planar geometry, the nucleophile can attack from either of the 2 directions that are perpendicular to the flat plane. Let's look at some SN1 examples now so we can see how we can use this rule to get the correct stereochemistry. Please pause the video and try this problem. Now we can discuss. I'll start by numbering the carbons. There's no ionic bonds, so no formal charges to place. We can identify some roles. We'll expect that the oxygen in the water will play the role of nucleophile, and the neutral bromine will be our leaving group. Carbon 3 will be our alpha carbon, and that's a secondary alpha carbon. Now we can use our table to determine the mechanism. Secondary alpha carbon puts us in the middle row of the table. And water, a neutral oxygen, puts us in the left-hand column of the table. So the major mechanism will be SN1. Make sure that you write that down, SN1. I think this is the first example where we've used this cell of the table. Middle row, left column, SN1. Now we want to draw our electron pushing arrows. Well, we have to remember that the first thing that happens in an SN1 is that the leaving group leaves. So we expect this first step to be a leaving group step, because we've memorized that the first thing that happens in an SN1 is that the leaving group leaves. Now we can draw the product from that step. This arrow tells us to break the bond between carbon 3 and the bromine. Remember to change your charges. Change two charges. Carbon 3 started neutral and it lost electrons, so carbon 3 becomes positive. And the bromine started neutral and gained electrons, so the bromine becomes negative. Now in our next step, we know that we need our nucleophile to attack the alpha carbon. Carbon 3 is a positive carbon, so that makes carbon 3 our electrophile. So in this step, our nucleophile will attack the alpha carbon. So that makes step 2 a nucleophile electrophile step. Now we can draw the products from that step. Now, this arrow tells us to draw a new bond between this oxygen and carbon 3. But should we show that the oxygen is going to end up on a wedge or a dash or a solid line on carbon 3? Well, we can use the rules that we've talked about previously. Here's the rules that we've talked about. Well, do you see how this rule doesn't apply for this problem? We would apply this rule if the atom that was being attacked was attached to the leaving group. But notice when the nucleophile attacks carbon 3 is no longer attached to the leaving group. So this rule is not applicable when the nucleophile is attacking carbon 3. Carbon 3 was attached to the leaving group in this picture, but the nucleophile wasn't attacking yet. By the time the nucleophile attacks, the leaving group is no longer attached. Instead, we'll use this rule because we should recognize that in this picture, carbon 3 is a carbocation with trigonal planar geometry. In this picture, when it gets attacked, the carbocation on carbon 3 has trigonal planar geometry. We've learned that carbocations have trigonal planar geometry, and that means that the nucleophile can attack from either of the two directions that are perpendicular to the plane. So the plane here is the plane of the page. Carbon 2 is in the plane of the page, carbon 4 is in the plane of the page, and if we drew the hidden hydrogen would also be in the plane of the page. That means that the water can attack from either in front of the page or from behind the page. Notice that there's no particular reason why the water should prefer to attack from in front or from behind, so we would expect that the water would attack from in front about 50% of the time and from behind the page about 50% of the time. So about 50% of the time, the water is going to end up on a wedge. About 50% of the time, the water will attack from in front of the page and end up on a wedge. About 50% of the time, it will attack from behind the page and end up on a dash. Now remember, the most important part to get right here is the charges. The oxygen started neutral and it lost electrons, so the oxygen should end up with a positive formal charge. And make sure that you show that the oxygen is still covalently bonded to these two hydrogens. So notice that to show the mechanism correctly here, we have to show a fork in the mechanism. We have to show that the mechanism forks or branches into two separate branches because there's two separate outcomes here. That's what I meant when I said the nucleophile can attack from either of the two directions. In a sense, that means the nucleophile will attack from both directions, sometimes from one direction and sometimes from the other direction. We'll follow this path about 50% of the time, and we'll follow this path about 50% of the time. Now we've seen how we can use this rule to correctly show the stereochemistry for an SN1 reaction. Now, are these the final products? Well, no, because they still have formal charges. We're probably not done since there's still a formal charge. We probably have to do another step, and that's probably going to be an acid-base cleanup step. You can use another water molecule as the base. We expect the positive oxygen to be acidic. A positive charge is a good sign of an acid, and we've learned that neutral oxygen with a lone pair can be basic. In fact, this oxygen is a better base than the Br-, as we've discussed. So now we can draw the electron pushing arrows for that step from the base to the proton. Electron pushing arrows go from the base to the proton, and then another arrow showing how the acid is gaining electrons to lose the proton. Now we can draw the products from that step. Make sure that you remember to change the charge on this oxygen from neutral to positive. Notice that because the mechanism now has two separate branches, the best way to draw this acid-base cleanup step is to draw it twice, once on this branch and once on this branch. This is the most accurate way to show what's happening now in the mechanism. Remember, why is this called acid-base cleanup? What's getting cleaned up? This is called a cleanup step because we're cleaning up this formal charge on the oxygen. So does it seem like we're done, or does it seem like we need another step? Well, now our main products have no more formal charges, so it seems like we're finished. We weren't able to get rid of the formal charge here or here, but our main products have no formal charges, so it looks like we're probably done with our mechanism. And we can say that these are our answers. These are the major products that the professor would probably be interested about on this problem. The professor likely would not be interested in this product or this product, but you should still draw the products as part of your mechanism for your own understanding. If this was a mechanism problem, on a mechanism problem, it would be important to include these products. On a problem that just asks you for the products, the professor is probably only going to grade you on these two products, but as I said, you should draw the other products as well for your own understanding. Okay, so the purpose of this problem was to show us how to show the stereochemistry for an SN1 reaction. And we can see how we can use this rule for an SN1 reaction. In an SN1 reaction, the nucleophile will attack a carbocation. Carbocations have trigonal-planar geometry. Planar means flat. So in an SN1, the nucleophile can attack from either of the two directions perpendicular to the plane. Usually that means it can attack from either in front of the page or from behind the page. So we can get one product where the nucleophile ends up on a wedge and another product where the nucleophile ends up on a dash. I should have mentioned that carbon-3 is a stereocenter. We're only going to get two separate products when we're attacking a stereocenter. You can see carbon-3 is a stereocenter in the original starting material because it's attached to four different groups: the bromine, the hidden hydrogen, a methyl group, and an ethyl group. Here is the rule that summarizes stereochemistry for an SN2. Can you come up with a similar rule for SN1? What rule would you write down to summarize the stereochemistry for SN1? Well, here's an answer. Well, here's one good way to summarize it. When we're dealing with an alpha carbon that's going to be a stereocenter, the products will have 50% inversion of configuration and 50% retention of configuration. Do you see which is which here? I would call this picture a picture with retention of configuration because the OH is on a wedge, the same position that the leaving group was on, retention of configuration. And I would call this picture a picture with inversion of configuration, because here the OH is in the opposite position to where the leaving group was. So here's our 50% retention of configuration, and here's the 50% inversion of configuration. By the way, remember that even though we only drew this starting material once, there are many billions upon billions of these molecules floating around in the solution. So this reaction is not happening just once in the solution, right? It's happening many billions upon billions of times. Of all those billions upon billions of times that the water is going to be attacking this starting material, about 50% of those attacks will end up with retention of configuration, and about 50% will end up with inversion of configuration. So you will get a mixture of products. You'll get a mixture of products where about 50% of these products have retention of configuration and about 50% have inversion of configuration. Exam problems frequently test the difference between SN2 stereochemistry and SN1 stereochemistry. So now is a good time to pause and memorize these key facts. This is the key rule for SN2 stereochemistry, and this is the explanation for this rule. This is the key rule for SN1 stereochemistry, and this is the explanation for this rule. It's good to know about these explanations because these explanations can come in handy not just in this part of the course, but also when you're studying later reactions in the course as well. By the way, did you notice that this problem just asked us for the products? It didn't actually ask us for the mechanism. So with these instructions, you wouldn't be graded on this mechanism. In fact, you don't actually have to draw the mechanism for this problem at all. But as a beginning Ochem student, I would encourage you that you should draw the mechanism. As a beginning Ochem student, you should generally draw the mechanism even if the problem doesn't ask you for it, because the mechanism is your tool for getting the correct products. So at this point, you should be drawing the mechanism for almost every problem, regardless of whether the problem specifically asks you for it or not. So here is a good way to draw the mechanism when you're doing an SN1 at a stereocenter. Here's a good way to show the mechanism when you're doing SN1 at a stereocenter. Please pause the video and try this problem. Now let's discuss together. By the way, the instructions for this problem are to draw the substitution products. The first time I recorded this video, I used different instructions. The first recording of this problem, I said the instructions were, draw the major products. But after I recorded that, I realized that for this problem, it would make more sense to say that I'd like you to draw the substitution products. So please disregard these instructions and just treat these as the instructions for the problem. We can start by numbering all the carbons, including these two carbons and including these carbons. Now we can identify roles. We look to see that there's no ionic bonds, so there's no formal charges that we need to apply. Now we can look for roles. We can use this neutral oxygen in the alcohol as the nucleophile. I hope that you recognized that this is a way of drawing an alcohol, an OH group attached to a carbon chain. And we have a neutral bromine, which we know we can use as our leaving group. And that makes carbon 1 the alpha carbon. That means we have a secondary alpha carbon, because the two different paths around the ring count as two different carbon chains attached to carbon 1. There's one carbon chain around the ring starting with carbon 2 and another carbon chain around the ring starting with carbon 5. That counts as two attached carbon chains, which makes carbon 1 a secondary alpha carbon. Now we can choose our mechanism. Secondary alpha carbon puts us in the middle row. And neutral oxygen and an alcohol puts us in the poor nucleophile column, so the major mechanism will be SN1. The table says that in this case we can get SN1 major and E1 minor, but the instructions say to draw the substitution products. So substitution products would come only from SN1, not from E1. Remember, the S in SN1 stands for substitution. By the way, the E in E1 stands for elimination. If they asked you for elimination products, you would follow the E1 mechanism here. But since they're asking for substitution products, we're drawing the SN1 mechanism. So now we can say that the first step is going to be a nucleophile, it's going to be a leaving group step, right? We know SN1 starts with a leaving group step. The first step of SN1 is that the leaving group leaves. Now we can draw the product of that step. Keep numbering all the carbons. Make sure you change 2 charges. Carbon 1 started neutral and lost electrons, so carbon 1 becomes positive. And the bromine starts neutral and gains electrons to become negative. Now it seems like we're not done because our main product still has a formal charge. So we need another step. We expect that step 2 of a SN1 reaction is going to be our nucleophile electrophile step. And it looks like I forgot to make a note that we're doing an SN1 mechanism. Always write down the name of the mechanism, because otherwise you might easily forget and accidentally do an SN2 when you meant to do an SN1. All right, now with the positive charge on a carbon, we know that a carbocation is electrophilic. So we expect carbon 1 to be our electrophile. And now we can draw the electron pushing arrow going from the nucleophile towards the electrophile. And draw the product of that step. This arrow tells us to draw a bond between the oxygen and carbon 1 because it starts on the oxygen and points to carbon 1. But should this oxygen end up on a wedge or on a dash? Well, we know that the geometry of this carbocation is trigonal planar. And when we attack something that's trigonal planar, we can attack from either direction. A carbocation is trigonal planar, so the nucleophile can attack from either of the 2 directions, either from in front of the page or from behind the page. So this is a point where our mechanism is going to fork, and we'll get 2 products. One where the nucleophile attacked from in front of the page and one where it attacked from behind the page. If the oxygen attacks from in front of the page, it'll end up on a wedge. But if the oxygen attacks from behind the page, it'll end up on a dash. Now, what else should this oxygen be attached to? Should the oxygen still be attached to this hydrogen? Yes, because it's covalently bonded to the hydrogen, and we would not break that covalent bond unless there was an arrow telling us to break that covalent bond. And should the oxygen still be attached to carbon 9? Yes, because the oxygen is covalently bonded to carbon 9. By the way, any bond that's represented by a solid line is considered covalent. That's one way we know this is covalent. In any way we would expect a non-metal bond to be covalent. So this is wrong. This is wrong unless we show that the oxygen is still bonded to carbon 9, which is still bonded to carbon 8. Here's where it's helpful to put in the numbers. If you don't put in the numbers, you could accidentally get the wrong number of carbons. If you don't put in the numbers, it would be easy to make a mistake like this and accidentally add a carbon. So instead, put in some numbers so that you're making sure you get the exact right length of carbon chain. Notice this is not carbon 8. This is not carbon 8. Carbon 8 shouldn't be attached to the oxygen. Carbon 9 is attached to the oxygen. Make sure you're numbering all your pictures consistently with each other. But I still haven't done the most important thing, which is the charges. The oxygen's at the beginning of the arrow, so it has to change charge from neutral to positive because it lost electrons. The most common student mistake here is forgetting to change the charge on this oxygen to positive. And of course, carbon 1 changes from positive to neutral. I've already made that change. So here again, we used the idea that when we attack a carbocation that has trigonal planar geometry, the nucleophile can attack from either of the 2 possible directions. Is the mechanism finished, or do we need another step? Well, there's still a formal charge on the main product, so it seems like we probably need another step. Oh, before I forget, another issue with these products, should we have changed the configuration at these carbons? Should we change this from a wedge to a dash? Should we have it sometimes on a wedge and sometimes on a dash? Should we do anything to change the geometry or change the stereochemistry at these carbons? No, because these carbons are not participating in the reaction. These carbons are not participating in the reaction. You can see that they're not participating because there are no electron pushing arrows dealing with these carbons. In particular, there's no electron pushing arrows dealing with carbons 3 and 4. So there's no reason to change the configurations at carbons 3 and 4. So that's one of the traps on this problem. One of the traps here is that the professor is hoping that students might try to make a change in the stereochemistry at carbon 3 or 4, but that would be a mistake because carbons 3 and 4 don't participate in the reaction. They don't participate because they weren't attached to leaving groups. Now we need another step because we still have a positive formal charge. Well, we expect that if we do a nucleophile-electrophile step and we still have a positive charge or any type of formal charge, we probably need an acid-base cleanup step. We expect that because these have positive charges, the oxygens will be the acids. We can say they will be strong acids because of their positive formal charges. So we need a base. We're not going to use the Br- as the base because Br- is a very weak base. Instead, we'll use the alcohol as the base. The alcohol is the solvent, so we don't need to worry about running out of it. So we can write down another copy of that same alcohol molecule. But this time, instead of using the alcohol as a nucleophile, now we're going to use it as a weak base. Neutral oxygen is a weak base. That's good enough to react with a strong acid. Remember that the electron pushing arrows go from the base, the electron donor, towards the proton that the base is taking. So you have to draw this hydrogen separated out so we can see its bond. Then we need a second arrow to show the acid receiving electrons to lose the proton. And we draw the same arrows for this branch of the mechanism. Now we can draw the products from that step. This arrow tells us to draw a bond between the oxygen and the hydrogen. So I'll show that new bond by showing this as OH2. The most important thing is to remember to change the charge on the oxygen. The oxygen started neutral and it lost electrons, so the oxygen becomes positive. Don't forget to change that charge. This arrow tells us to show that the bond has broken between this oxygen and the hydrogen. So here we show that the oxygen has lost its bond to the hydrogen, and of course we change the charge on the oxygen from positive to neutral. All right, now the problem was asking for the substitution products. The professor probably wouldn't care about this product or this product here. By the substitution products, the professor probably wants these two products. So here would be our answer for this problem. The purpose of this problem was to give us more practice with SN1 stereochemistry. So we saw that in SN1 stereochemistry, the nucleophile attacks a trigonal-planar carbocation, so it can attack from either direction. So we'll get one product with inversion of configuration and one product with retention of configuration. By the way, on a problem like this, the distribution of the products might not be 50-50. There might not be 50-50 because it might be harder for this nucleophile to attack from in front of the page because it might be partially blocked by these two methyl groups that are both pointing in front of the page. Because these two methyl groups are both pointing in front of the page, the OH can attack from in front of the page, but maybe it'll attack more often from behind the page. So maybe with this example, we might not get a 50-50 split. Maybe with this example, we might get more of the OH attacking from the less hindered side of the molecule behind the page, and less of the OH attacking from the more hindered side in front of the page. So this 50-50 outcome only applies to simple cases. We would still expect, though, that we would get a mixture with some retention of configuration and some inversion of configuration. So we should include both of these in our answer. We should include both of these in our answer, even though they might not be produced in equal amounts in this reaction. By the way, that's why I changed the original instructions for this problem. The first time I wrote the problem, I said that you should draw the major products, but that is a little bit ambiguous. Because we might expect that we would get more of this product than this one. And I really wanted you to show both of them. So to avoid that issue, I changed the instructions to say just draw the substitution products. In that case, we should definitely draw both of these products, even if we expect we might get more of this substitution product than of this one. Now notice that we did not get any change of configuration at these carbons because they weren't participating in the reaction. That's why in this rule I said that we get inversion of configuration at the alpha carbon and retention at the alpha carbon. It's only the alpha carbon that we expect to have any changes in this reaction. So we have 50% inversion and 50% retention at the alpha carbon. If there are any other carbons with interesting geometry, their geometry is not going to change in the reaction because they're not participating as the alpha carbons. That's one reason why it's a good idea to label the alpha carbon. Carbon 1 is the alpha carbon for this reaction, so carbon 1 is the carbon whose stereochemistry is affected by the reaction. Carbons 3 and 4 are not the alpha carbons for this reaction, so their stereochemistry is not affected by the reaction. Now, let's try to get a deeper insight into what happened here by thinking about the hidden hydrogen. You'll understand what's happening here with SN1 stereochemistry better if you also draw what's happening to the hidden hydrogen in these pictures. First of all, taking a look at carbon 1, how many hidden hydrogens are there on carbon 1? Well, carbon 1 is a neutral carbon in this picture. A neutral carbon should have 4 bonds. We already see 3 bonds, so there should be 1 hidden hydrogen. Now, where should I draw that hidden hydrogen? Well, carbon 1, a neutral carbon attached to 4 different things, is a tetrahedral carbon, and we know the right way to draw a tetrahedron is with a solid line, another solid line, a wedge, and a dash. So here we've drawn in the hidden hydrogen on the dash. This is the correct way, remember, to show tetrahedral geometry. 2 solid lines, a wedge, and a dash. If we drew the hydrogen on a wedge, that would be a mistake. We shouldn't have 2 wedges here. And if we drew the hydrogen on a solid line, that would be a mistake. We shouldn't have 3 solid lines. Tetrahedral geometry is 2 solid lines, a wedge, and a dash. Tetrahedral geometry is 2 solid lines, a wedge, and a dash. That's the usual way to draw tetrahedral geometry. Now, please pause the video and draw the hidden hydrogen in this picture on the carbocation intermediate. I hope you actually paused and drew the hidden hydrogen on this carbocation intermediate. Where should that hydrogen be? Well, what's the geometry of the carbocation? Remember, the carbocation should be trigonal planar. That means that if you drew the hydrogen on a dash, you made a mistake. A trigonal planar picture shouldn't have a dash. Remember, to show that it's trigonal planar, we should show all 3 bonds in the plane of the page, all 3 bonds as solid lines. So the correct way to show this hydrogen is on a solid line. That is, the position of the hydrogen has changed from this picture to this picture. In this picture, the hydrogen was behind the plane of the page. But when we changed from a tetrahedral carbon to a trigonal planar carbocation, the geometry at carbon 1 has changed. So the position of carbon 1 has changed, the hydrogen has changed. Now the hydrogen is in the plane of the page, the same plane as carbon 2 and 5. That's why this is called planar. It's called planar because all 3 attached atoms are in the same plane, the plane of the page. And of course, we could think of it as being trigonal because there's 3 different attached atoms attached in that plane. Okay, so the hidden hydrogen changes here from a dash to a solid line. And I think you can see here then that this alcohol can now attack from either in front of the page or from behind the page. Most students get this step wrong. Most students, I think, here would still draw the hydrogen on a dash. So I hope you can see why when we change from a tetrahedral to a trigonal planar geometry, the hydrogen changes from a dash to a solid line. that gives us a better understanding of what's happening with the geometry at this carbocation. So now you can draw the hidden hydrogen on carbon 1 in these pictures. Pause the video and draw the hidden hydrogen in these pictures. Well, notice that in these pictures, we've gone back to a neutral carbon, so we've gone back to tetrahedral geometry. Here we are back with tetrahedral geometry, where we should have two solid lines, a wedge, and a dash. In this picture, the oxygen is on the wedge, so the hydrogen must be on the dash. And in this picture, the oxygen is on a dash, so the hydrogen must be on the wedge. How did the hydrogen end up in those positions? Well, in this branch of the mechanism, the alcohol attacked from in front of the page. So when the alcohol attacked from in front of the page, it pushed the hydrogen back behind the page, so that the hydrogen ended up behind the page. On the other hand, in this branch of the mechanism, in this branch, the alcohol attacked from behind the page. Since the alcohol was attacking from behind the page in this branch, while the alcohol attacked from behind the page, it pushed the hydrogen forward to point in front of the page. So the hydrogen will be pushed either behind the page or in front of the page, depending on which direction the nucleophile attacks from. Now show the hidden hydrogens in this picture. Well, that should have been easy. There's no change in the geometry of carbon 1 from here to here. So the hydrogen should be in the same position in this picture as in this one. The hydrogen stays on a dash in this branch, and the hydrogen stays on a wedge in this branch. Okay, and now I think you can see more clearly that this is the branch that gives us retention of configuration, and this is the branch that gives us inversion of configuration. In this branch of the mechanism, the hydrogen is in the same position that it started in. The hydrogen started on a dash and it ended on a dash in this branch. The hydrogen has retained its position, so we would call this branch the branch that shows retention of configuration. And in this product, the hydrogen has ended up inverted from where it was before. In this picture, the hydrogen was behind the page, and here it's changed to in front of the page. So I think that makes it clearer how we have inverted the configuration around carbon 1 in this branch of the mechanism. Now, you absolutely do not have to draw the hidden hydrogen on carbon 1. You don't have to draw the hidden hydrogen on carbon 1. In fact, usually, it's probably better not to draw that hydrogen. It's probably better not to draw the hydrogen just because it adds extra clutter and complication to your pictures. Normally, it would probably be best not to draw the hidden hydrogen on carbon 1, but I thought it was a good exercise. I thought it was a good exercise for this one example to draw in the hidden hydrogen, just so that we could get a better intuitive understanding of how the geometry of carbon 1 is changing from the starting material to the carbocation and then back to the products. Hopefully now you have a better understanding of how we change from a tetrahedral geometry to a trigonal planar geometry and back to a tetrahedral geometry. So the big idea we saw here is that the geometry of the carbocation really is different from the original geometry in the original starting material. A trigonal planar geometry really does look different than a tetrahedral geometry. We got some practice with these ideas that a tetrahedral geometry is drawn with two solid lines, a wedge, and a dash, whereas a trigonal planar geometry is drawn with three solid lines. Please pause the video and try this problem. Now we can discuss. Now the first thing we have to do is identify what this group is. We haven't seen a group like this before in this video series. I hope you were able to identify that this is a sulfonate group. I talked in detail about sulfonates in one of the videos in the SN2 series. So if you are not familiar with sulfonates at all, you might want to go back and watch that earlier video on sulfonates. But we'll also briefly illustrate how to handle a sulfonate in the solution we're going to go through right now. Technically, this molecule is what we would call an alkyl sulfonate. Alkyl means carbon chain. So an alkyl sulfonate is a carbon chain attached to a sulfonate. A carbon chain attached to a sulfonate. This part is the sulfonate. And this part is the alkyl group referred to in the name. Notice that a sulfonate has a sulfur connected to three oxygens. A sulfur connected to three oxygens. Also, do you realize that this carbon is not attached to either of these two oxygens? This carbon is attached to this sulfur. That's something that's really plainer if you've just memorized what a sulfonate really looks like. So this is a condensed notation that's showing that the two oxygens and this carbon ring are all attached to this sulfur. Now we need to identify the alpha carbon. You should have memorized that in an alkyl sulfonate, the alpha carbon is the carbon attached to the oxygen, not the carbon attached to the sulfur. So that tells us that this is the alpha carbon. This is the alpha carbon because this is the carbon that's attached to the oxygen. This is not the alpha carbon because this carbon is attached to the sulfur. That might not be obvious from this condensed notation, but this carbon is attached to the sulfur, and therefore it's not the alpha carbon. You should memorize that in an alkyl sulfonate, the alpha carbon is the carbon attached to the oxygen, not the carbon attached to the sulfur. The important thing about a sulfonate is that sulfonates are good leaving groups. So this sulfonate is going to be considered to be a good leaving group. All right, so now we can attack the problem. I can number the carbons. It's important to number all of these carbons to make sure we don't make a mistake copying this carbon chain. It's probably not necessary to number these carbons. These are so, we're not likely to make any mistakes with these carbons in the sulfonate, but you should definitely number all these carbons outside of the sulfonate. We should look for ionic bonds. Well, there are no ionic bonds here, so there are no formal charges to draw in. Notice the sulfonate is completely covalently bonded. No formal charges. Now we can assign roles. We'll expect that the oxygen in this alcohol will be our nucleophile. And remember, we've learned that the sulfonate is a good leaving group. Now we want to identify which atom in the sulfonate is going to be the leaving group atom. Well, remember that the leaving group is attached to the alpha carbon. And we know this is the alpha carbon. That means this particular oxygen is the leaving group atom. We could say that this whole group is the leaving group, but it's also helpful to say that this particular atom, this particular oxygen, is the leaving group atom, because this is the one that's attached to the alpha carbon. Again, not one of these two oxygens. In the alkyl sulfonate, the alpha carbon is the carbon attached to the oxygen, which makes this oxygen the leaving group, and this carbon the alpha carbon. Those are things that are useful to have memorized about a sulfonate. So now we can choose our mechanism. Oh, it looks like I didn't number all the carbons. I should really number this carbon. This molecule will be participating in the reaction, so it's useful to number its carbon as well. Now we can choose the mechanism. Well, our alpha carbon is tertiary. Let's write that down. You see why this alpha carbon is tertiary? It's attached to 1, 2, 3 carbon chains. Count the carbon chains. That puts us in the bottom row of our table. Our nucleophile is the neutral oxygen in an alcohol. That puts us in the left-hand column of our table. So we predict that the major mechanism will be SN1. There will be E1 minor, but the question's asking for the major mechanism, so we'll just draw the SN1. Make sure that you write down the name of the mechanism, SN1. By the way, have you noticed the title of this table? You can see that this table is relevant for alkyl sulfonates. This table works for alkyl halides and alkyl sulfonates. So this is the first example that we've done in this video series where we applied the table to an alkyl sulfonate. All the previous examples in this video series, we applied the table to alkyl halides, carbon chains attached to halogen leaving groups. So this table usually works for both alkyl halides and, as in this case, for an alkyl sulfonate. Now we can try drawing the arrows. We know that the first step is going to be a leaving group step. We start with the leaving group step. Remember again, this is the alpha carbon, and the oxygen is the leaving group atom. So the correct way to draw the electron pushing arrow for this sulfonate is like this. You definitely would not do something like this. This would be wrong. This is not the alpha carbon. So that's the correct arrow for that leaving group step. So we have seen that in an alkyl sulfonate, the sulfonate group is a good leaving group. And notice that the sulfonate leaving group is neutral before it leaves. Now, that is consistent with this summary of roles in Ochem that we saw in the first video in this series. So this tells us that neutral chlorine, bromine, and iodide are acceptable leaving groups, and it also tells us that neutral sulfonates are also acceptable leaving groups. You should know that neutral atoms are usually not acceptable leaving groups unless you've specifically learned otherwise. So we should specifically learn that similar to neutral chlorine, bromine, and iodine, we should specifically learn that neutral sulfonates are acceptable leaving groups, even though most other neutral atoms are not acceptable leaving groups. Now we can draw the products from that step. This arrow tells us to break the bond between carbon-3 and the oxygen. So I've broken that bond between carbon-3 and the oxygen. I've broken the oxygen away from carbon-3. Make sure you change two charges. Carbon-3 started neutral and lost electrons, so carbon-3 becomes positive, and the oxygen becomes negative. But do you see, this picture is still not right because it's not showing the correct geometry at carbon-3. In this picture, carbon-3 was tetrahedral, but now carbon-3 is a carbocation, so in this picture, carbon-3 should be trigonal planar. But if carbon-3 is planar, we should not have a group pointing behind the page. We can't use a dash to show a planar carbocation. The geometry of carbon-3 has changed. Therefore, carbon-6 has to move into the plane of the page to be planar with carbon-2 and 4, so carbon-6 should now be drawn on a solid line. Carbon-6 should now be drawn on a solid line to show that it's in the same plane as carbons 2 and 4. We've changed from a tetrahedral geometry to a trigonal planar geometry. Now, this particular problem isn't grading you on the mechanism, but you'll have better understanding of this problem if you're drawing the mechanism, and drawing it correctly. So let's draw the geometry correctly here to show that we've changed to a planar geometry where carbon-6 is on a solid line. That's an aspect of the mechanism that I find most students get wrong. Okay, well, we're not done because our main product has a formal charge, so now we're ready for step 2, which is going to be our nucleophile electrophile step. That's what we expect for step 2 of a SN1 reaction. So now we use the nucleophile and have it attack the alpha carbon. The nucleophile attacks the alpha carbon. This arrow tells us to draw a bond between the oxygen and carbon-3. Now, because we're attacking something trigonal planar, the oxygen can attack from either direction. So let's say that in this branch, the oxygen will attack from in front of the page. Then the oxygen will end up on a wedge, which will push carbon-6 backwards to a dash. I showed the oxygen attacking from in front of the page, so the oxygen ends up on a wedge. Now, as the oxygen comes in from in front of the page, it's going to push carbon-6 behind the page. So carbon-6 ends up on a dash. Make sure you change the charges. The oxygen started neutral and it gained electrons, so this oxygen should end up with a positive formal charge. It would be a big mistake to leave out that positive formal charge. And of course, I've already changed the charge here on carbon-3 from positive to neutral. So it would be a mistake here to leave carbon-6 on a solid line. In this picture, carbon-6 was on a solid line to show that the carbocation was trigonal planar. But now in this picture, we've gone back to a tetrahedral geometry. Since we've gone back to a tetrahedral geometry here, carbon-6 should no longer be on a solid line. Now carbon-6 should be on a dash. And again, we have two solid lines here, a wedge and a dash. Now we expect that because this was trigonal planar, the oxygen could also have attacked from behind the page. If this oxygen attacks from behind the page, then the oxygen will end up on a dash, and that will push carbon-6 forward to a wedge. Here we have the oxygen attacking from behind the page, which pushes carbon-6 in front of the page. Again, carbon-6 is no longer on a solid line in this picture. Again, make sure you change the charge on the oxygen to positive. These are pretty complicated products, so I think it's really important to make sure that you number all the carbons. If you don't number all the carbons, it's easy to accidentally add or drop carbons in these pictures. Actually, I can see I didn't quite follow my own advice there. I should keep numbering carbon 8 as well. So here's carbon 8 in this picture and carbon 8 in this picture. Of course, this oxygen should stay bonded to carbon 8 and stay bonded to this hydrogen in these pictures. Don't forget to draw the hydrogen and carbon 8 in those pictures. There's no reason to break those covalent bonds. All right, so here we have the key step for showing the stereochemistry for the SN1. Most students don't get this mechanism right. Most students don't realize that carbon 6 should change from a dash in the starting material to a solid line in the trigonal-planar carbocation intermediate. And then if a student got that right, they might forget that after the nucleophilic attack, carbon 6 should go back to a dash or to a wedge and not stay on a solid line. We're changing from tetrahedral geometry to trigonal planar geometry and then back to tetrahedral geometry. So the position of carbon 6 changes in each of those pictures. All right, now we need an acid-base cleanup to get rid of our positive charge. We expect the positive oxygen will be a strong acid. The positive oxygen will be our strong acid. Who are we going to use as our base? You might be tempted to use this sulfonate group as the base since it has a negative formal charge. But this negative sulfonate is like the negative Br minus or negative I minus or negative Cl minus that we've learned about. It's a very weak base, so we'd be better off using the alcohol solvent as the base rather than the sulfonate. Why is the sulfonate such a weak base? Can you figure out why the sulfonate is such a weak base? It's easier to understand that if I draw the less condensed structure. So here's a less condensed structure for this sulfonate. Why don't you pause the video and try to determine why this sulfonate is such a weak base? Well, it's the same reason that the sulfonate was a good leaving group. This sulfonate is a good leaving group because after it leaves, the negative charge is stabilized by resonance. There are two other resonance structures for this sulfonate that can put the negative charge on this oxygen or on this oxygen. After the sulfonate leaves, the negative charge is stabilized by resonance, and that's what makes it easy for the sulfonate to leave in the first place. It's easy for the sulfonate to leave in the first place because after it leaves, its negative charge is stabilized by resonance. Well, since this negative charge is stabilized by resonance, it's a stable negative charge, which makes it less necessary for the sulfonate to donate electrons. And remember, that's what a base does. Remember that a base donates electrons to take a proton. A base is an electron donor. The negative charge makes the sulfonate want to donate electrons, but it's not that eager to donate electrons because the negative charge is resonance stabilized. Because this negative charge is resonance stabilized, it's not that important to the sulfonate for it to donate electrons, and as a result, it's a very weak base. So we'd probably be better off using the alcohol as the base here rather than the sulfonate. I talk in more detail about the role that resonance plays with sulfonates in that earlier video in the SN2 series. But you can understand the key properties of a sulfonate if you understand that the negative charge on a sulfonate after it leaves is resonance stabilized. That explains why the sulfonate is a good leaving group, and it also explains why it's a pretty weak base. Here are the electron pushing arrows for this acid-base cleanup. I hope you're getting comfortable with the idea that the first arrow for acid-base step goes from the base to the proton. The base is donating electrons to take a proton. And don't forget the second arrow as well. Now we can draw the products from that step. So this arrow tells us to form a new bond between the oxygen and the hydrogen. So the oxygen changes to an OH2. And we break the bond between this oxygen and the hydrogen. The most important thing is to remember to change this charge. This oxygen is at the beginning of the string of arrows, so this oxygen changes from neutral to positive. And of course, the charge on this oxygen, I've already changed that from positive to neutral. Now our main products have no charge, so it looks like we're probably done with the reaction. So our major products would be these. here would be our answer to the problem. This is the first problem in this series where we've dealt with a sulfonate leaving group. So we saw this is the general structure for a sulfonate. You need to know that in a sulfonate, the alpha carbon is the carbon attached to the oxygen, not the carbon attached to the sulfur. That's how we knew carbon 3 was the alpha carbon in this case, not this carbon. You need to know that sulfonates are good leaving groups. We also got more practice with SN1 stereochemistry, and in particular, how to show how the stereochemistry changes for the carbocation intermediate. In this picture, carbon 6 was on a dash as part of the tetrahedral geometry. Then carbon 6 changed to a solid line as part of the trigonal planar carbocation. And then in this picture, carbon 6 changed to either a dash or to a wedge as the geometry reverted back to a tetrahedral geometry. By the way, these are not the only possible correct ways to draw the products. There's always multiple correct ways to show stereochemistry. So it's possible that the answer key might show the answer somewhat differently than this, or you might have come up with your own answer that looks different than this. So unfortunately, there are multiple correct possible answers here because there's multiple correct ways to show these two molecules. I think that these are probably the simplest and best ways for a beginner. For a beginner trying this problem, I think these are the two best ways to draw the products. But if your product looks different from the answer key, how can you tell whether your answer is wrong or whether you've just drawn a different version of what's in the answer key? Well, if you're a good way to attack that is you can assign R and S. If you know how to assign R and S, you can assign R and S to your products and then assign R and S to the answer key. If you have the same pattern of R and S as the answer key does, then your answer matches the answer key. And if you have a different pattern of R and S than the answer key does, then you've made a mistake. Of course, that's only going to work if you are good at assigning R and S labels to stereocenters. So this is one possible way to draw the correct stereochemistry for the two products from this reaction. Please pause the video and try this problem. Now we can go through it. We can start by numbering all the carbons, including this one and including this one, but I'm not going to bother numbering this carbon. This is a part of the sulfonate that I'm unlikely to make any mistakes about. We should look for ionic bonds that would require us to draw in formal charges. There are no ionic bonds shown, no metals and no metals bonded to nonmetals. We can see there's already a formal charge drawn for us. There was already a formal charge drawn for us on this species, a negative formal charge. We can assign roles. We focus on the formal charge. Because the carbon has a formal charge, we expect it to be nucleophilic, an electron donor. Notice that the formal charge is on the carbon, not the nitrogen. So we expect the carbon to be the nucleophile. And we know that a sulfonate group is a good leaving group. It helps to identify the alpha carbon here. Remember, the alpha carbon is the carbon that's attached to the oxygen, not the carbon that's attached to the sulfur. In an alkyl sulfonate, the alpha carbon is the carbon attached to the oxygen, not the carbon attached to the sulfur. So we expect this oxygen attached to the alpha carbon to be the leaving group atom. So we're using, again, the ideas that we practiced in the previous problem, because this is another alkyl sulfonate group. Notice that there's more than one type of sulfonate. Here's one sulfonate with this benzene ring and an extra methyl group. And here's another sulfonate, a simpler sulfonate that just has a methyl group in this position. But those are both sulfonates. They're both parts of alkyl sulfonates. And the key thing is that both those sulfonate groups are good leaving groups, because both of them will be resonance stabilized after they leave. Our alpha carbon here is secondary. We have a secondary alpha carbon because it's attached to two carbon chains, a carbon chain starting with carbon 2 and another carbon chain starting with carbon 4. Now we can use our table to determine the mechanism. A secondary alpha carbon means we're using the middle row of the table. And our nucleophile is this CN-. And you can find that CN- here in the middle column. Here's the CN- in the middle column of our table. Good nucleophile and weak base. So since we're here in the middle column, the mechanism is SN2. By the way, we learned in the SN2 series that this is a common nucleophile called cyanide. This comes up a lot in Ochem, so it's worth knowing that the name of this nucleophile is cyanide. So the table tells us that the mechanism is SN2. Make sure that you write down the name of that mechanism. So this was an important problem. This problem was a kind of a trap. So far in this video series, we've been doing lots of SN1 problems. And so I want to make sure that you're not assuming that all the problems are SN1, because obviously when you take your exams, the problems will be a mixture of many different mechanisms. So I hope you didn't assume that this problem would be SN1. So did you fall into the trap, or did you correctly determine that this was SN2? If you assume that this reaction was SN1, that means you're doing the problems too much on autopilot, and you need to be more careful to use the table to determine the mechanism. On the other hand, if you correctly saw that this was an SN2 mechanism, that's good work. So again, notice how we used the table to determine that the mechanism here is not SN1, but SN2. We're in the middle row because we have a secondary alpha carbon. And we're in the middle column because cyanide, CN-, is our nucleophile, SN2. Well, now you need to refresh your memory what happens in an SN2 reaction. Do you remember how many steps are there in an SN2 reaction? You should recall there's one step in an SN2 reaction. Do you remember what happens in that one step? I hope you remember. In an SN2 reaction, in the one step, the nucleophile joins the alpha carbon, and simultaneously the leaving group leaves the alpha carbon. So we can say that we know that our step here is going to be a nucleophile electrophile step. And we can continue to assign our roles. We've already assigned nucleophile and leaving group. We need to find, and we know the alpha carbon will be the electrophile. What's the clue that this carbon is electrophilic? Well, carbon 3 is attached to the oxygen. Oxygen is to the right of carbon in the periodic table, which means that oxygen is more electronegative than carbon, which means that oxygen wants electrons more than carbon, which means that the oxygen is going to pull the electrons in this covalent bond closer to the oxygen and further from carbon 3, which will leave carbon 3 with a delta positive charge. The delta positive charge on carbon 3 is the clue that it's electrophilic. Previously in this video series, we've seen that when there's a positive formal charge on a carbon, that's a good sign of an electrophile. But when you don't have a positive formal charge, another clue for an electrophile is a delta positive charge. And that's what we're using here for this SN2 reaction. Here, so here's a summary. Here's a summary of clues that you should look for electrophiles. A positive formal charge on a carbon, or if you don't have a positive formal charge, a delta positive charge. These clues should both make sense because positive charges, it makes sense that a positive charge would make you more eager to receive electrons. Now we can draw the electron pushing arrows. We know that in this step the nucleophile should be joining the alpha carbon. The nucleophile is the electron donor, so the electron pushing arrow goes from the nucleophile towards the electrophilic alpha carbon. But we have memorized that in an SN2 reaction, simultaneously the leaving group also leaves the alpha carbon. So in that same step, we have to draw another electron pushing arrow to show the leaving group simultaneously leaving the alpha carbon. So you can see this mechanism is different than an SN1 mechanism. In an SN1 mechanism, the leaving group would leave the alpha carbon before the nucleophile joins the alpha carbon. But in an SN2 reaction, the leaving group leaves the alpha carbon simultaneously with the nucleophile joining the alpha carbon. This problem didn't specifically ask us for the mechanism, but we know that we generally should draw the mechanism, even when we're not asked for it, as our tool for understanding the problem and for getting the correct product. Now we can draw the product of this step. Remember, don't start drawing the product until you've finished drawing all the electron pushing arrows for the step. This arrow tells us to form a bond between carbon 3 and carbon 7. I need to draw a new bond between carbon 3 and carbon 7, but should carbon 7 end up on a wedge or a dash or both? What's the rule to use? Well, previously in this video, we've been using this rule about what happens when a nucleophile attacks a trigonal planar atom. But this atom is not trigonal planar. This atom is tetrahedral. This is a neutral carbon attached to four things. It's tetrahedral, not trigonal planar. So this rule that we've been using previously is not applicable for this problem. Instead, do you see this rule is applicable? Because here we have a nucleophile attacking an atom while it's still attached to the leaving group. When the nucleophile attacks, the leaving group is still attached. So we're now using this rule, which says that the nucleophile will attack from the side opposite to the leaving group. Well, the leaving group was behind the page. Therefore, this nucleophile should attack from in front of the page. Therefore, the nucleophile will end up in front of the page on a wedge. We used this rule. The nucleophile attacked from the side opposite the leaving group, so the nucleophile ended up attached in front of the page. Notice that we're continuing to number all the carbons consistently with our old numbers. Now, should this carbon still be attached to this nitrogen? Absolutely, because these are covalent bonds. Bonds that are illustrated with solid lines are always covalent bonds, and we would not break these covalent bonds unless there was an arrow telling us to break them. Well, there's no arrow telling us to break these bonds, because there's no arrow that starts on the bonds, so the carbon will still be bonded to the nitrogen. You could draw that like this. You could draw that the carbon is still bonded to the nitrogen like this. But usually the way we deal with cyanide groups is we just condense the cyanide group and draw it like this. Usually we condense the cyanide group and draw it like this, although it's good to know in the back of your mind that there's actually a triple bond between the carbon and the nitrogen in the cyanide group. Make sure you change a charge. This carbon is at the beginning of the series of arrows. It started negative and it lost electrons, so carbon 7 changes to neutral. I've already made that change. This arrow tells us to break a bond. This is an arrow that does tell us to break a covalent bond between carbon 3 and the oxygen. I've really already broken that bond. And we should change a charge. The oxygen started neutral and it gained electrons, so the oxygen should end up with a negative formal charge. Always make sure that you change 2 charges for every mechanism step, at the beginning of the series of arrows and at the end of the series of arrows. We never change charges in the middle of the series of arrows, so we're not going to change the formal charge on carbon 3, which is in the middle of the series of arrows. Carbon 3 started with 0 formal charge, and carbon 3 ends with 0 formal charge. Also, don't confuse the formal charge system with the delta charge system. The arrows don't tell us how the delta charges change. We just don't really care what the delta charge on carbon 3 is in this picture. I guess carbon 3 wouldn't have much of a delta charge in this picture, but we don't care about its delta charge in any case in this picture. Again, don't confuse the delta charge system with the formal charge system. The electron pushing arrows tell you how to change the formal charges. You could figure out delta charges if you needed to by asking whether an atom is connected to something that has a different electronegativity than it does. And now we're done with the mechanism. An SN2 reaction has 1 step, and we've completed that 1 step. Here's the product that the professor would probably be interested in based on these instructions. So what are the traps on this problem? Well, one big trap is that since you've just done a bunch of SN1 reactions, it might have been tempting to try to do an SN1 mechanism here. So remember that on the exam, you're going to have to keep switching back and forth between SN2 and SN1 and all the other mechanisms that you'll be learning. So don't assume that the mechanism is SN1. Use the table to determine what the mechanism is. That made a difference because if this was an SN1 reaction, we would get 2 products. One where the nucleophile ended up on a wedge, and another where the nucleophile ended up on a dash. If we were doing an SN1 reaction, we would get two products. One product with inversion of configuration and one product with retention of configuration. But in fact, on this problem, we were using SN2. So we got just a single product with inversion of configuration. Remember that SN2 gives you inversion of configuration at the alpha carbon. So hopefully now you can see the important differences between SN1 stereochemistry and SN2 stereochemistry, and you can see why it's so important to know whether the mechanism is SN2 or SN1. That's why it's so important to use the table. Another trap on this problem is that the professor might be hoping that students will mistakenly try to change the configuration at carbon 1. We don't make any changes to the configuration at carbon 1 because carbon 1 is not participating in the reaction. Notice that SN2 gives you inversion at the alpha carbon. There's no reason for SN2 to invert the configuration at carbon 1. Carbon 1 is not the alpha carbon. It's not participating in the reaction. That's one good reason to label the alpha carbon. That's where the stereochemistry is going to change. This problem gave us some more practice working with a sulfonate leaving group in an alkyl sulfonate. It also gave us some practice with this cyanide nucleophile. Cyanide is a common nucleophile in Ochem, so you should be familiar with this cyanide group. Remember that, in fact, there's a triple covalent bond between the negative carbon and the nitrogen in cyanide, but it's acceptable to condense the formula for cyanide and just write it as CN. Notice that the nucleophilic atom in the cyanide is the carbon, not the nitrogen, because it's the carbon that has the negative formal charge, not the nitrogen. Remember, always write down the name of the mechanism. A big mistake that students oftentimes make is they figure out the mechanism, but then they forget what mechanism they figured out and they do the stereochemistry for the wrong mechanism. So to help you avoid that mistake, actually write down the name of the mechanism once you've figured it out. Remember, all these details that I'm writing down here are details that would be good for you to write down. It would be good for you to label the roles that the atoms are playing, for example, and the type of step, and label the alpha carbon and the type of alpha carbon. All these labels are helpful habits for a beginning Ochem student to use. Please pause the video and try this problem. Now let's discuss. We can start by numbering the carbons. You should number these carbons. I don't think we're likely to make any mistakes with these carbons, so to save time and clutter, I won't number these carbons. Also, do you know what Me stands for? I hope you know that Me is abbreviation for a methyl group. So this group also has a carbon, but it's difficult to number that when the group is written as Me, so I guess I won't number that either. Okay. For ionic bonds. There are no ionic bonds, no metal, non-metal bonds, so there's no formal charges we have to assign. Remember again, Me stands for a methyl group, and the methyl group would be covalently bonded to the oxygen. So this is covalently bonded, not an ionically bonded compound. Now we can try to assign roles. This is an alcohol. Remember, an alcohol is an OH group attached to a carbon chain. Again, this is a methyl group, so here we have an OH group attached to a carbon chain. This is an alcohol. We know that the neutral oxygen in the alcohol is nucleophilic because of its lone pair. We know that a neutral iodide can be used as a leaving group, which means that carbon 1 is our alpha carbon because it's attached to the leaving group. So what type of alpha carbon do we have? We have a tertiary alpha carbon. Carbon 1 is attached to 3 carbon chains. A carbon chain that starts with carbon 6, a carbon chain that starts with carbon 2, and a third carbon chain in the benzene ring. So carbon 1 is a tertiary alpha carbon. Now we can use our table to determine the mechanism. A tertiary alpha carbon puts us in the bottom row of the table. Neutral oxygen in an alcohol means that we're in the left-hand column of the table. And that means that the major mechanism will be SN1. There will be E1 minor, but they're asking for the major product, so we'll just draw the SN1. Make sure you write down the name of the mechanism, SN1. Now we can write down what type of step we're going to do first. We know that an SN1 reaction begins with a leaving group step, where the leaving group leaves. That's all that happens in the first step. The leaving group just leaves. So now we can draw the product from that step. This arrow tells us to break the bond between carbon 1 and the iodide. Break the bond between carbon 1 and the iodide. Make sure you change two charges. Carbon 1 started neutral and it lost electrons, so carbon 1 becomes positive. And the iodide will become negative. A common mistake would be forgetting to change the charge on carbon 1. Now this benzene group is still attached to carbon 1 because there's no arrow telling us to break this bond. But is it still on a dash? Well, notice that the geometry here has changed. In the starting material, carbon 1 was tetrahedral. But remember that carbon 1 is now changed into a carbocation, and a carbocation should be trigonal planar. That means all the bonds should be solid lines. So we have to change the bond to the benzene to be a solid line. A lot of students would miss this, but since we now have a trigonal planar carbocation, all three bonds should be solid lines. So the benzene changes from a dash in this picture to a solid line in this picture. Is the mechanism finished? Probably not, because the main product here still has a formal charge. So now we're ready for step 2. Well, we have memorized that step 2 of an SN1 reaction is a nucleophile-electrophile step, where the nucleophile attacks the alpha carbon. We've memorized that that's what happens. We expect to use this atom as the nucleophile, and we expect to use carbon 1 as the electrophile. What's the clue that carbon 1 is electrophilic? The clue is that it's a carbon with a positive formal charge. So now we can draw the arrow, electron pushing arrow, for that step. In step 2 of an SN1 reaction, the nucleophile attacks the alpha carbon. Now we draw the products of that step. This arrow tells us to draw a bond between this oxygen and carbon 1. Should the oxygen attack from in front of the page or from behind the page? Well, the oxygen is attacking a carbon that is trigonal planar. And we know the rule is that when you attack something trigonal planar, you can attack from both directions. So we expect the oxygen will attack from both in front of the page and from behind the page, which means that the mechanism has to fork. In this picture, I'll show the oxygen attacking from in front of the page. So the oxygen ends up on a wedge. And in this branch, I'll show the oxygen attacking from behind the page so that the oxygen ends up on a dash. Let's see. The oxygen should still be bonded to the hydrogen. That's a covalent bond that's not breaking. And the oxygen should still be bound to the methyl group. Remember that this is a methyl group. It would be covalently bonded to the oxygen, not ionically bonded. So there's no reason to break that covalent bond because there's no arrow telling us to break that covalent bond. So it's important that we show that the oxygen is still covalently bonded to the methyl group. Most important, get the charge right. The oxygen is at the beginning of the series of arrows. It started neutral and it lost electrons, so make sure that you mark the oxygen as positive. And carbon 1 changes from positive to neutral. We've already made that change. Now, what about this benzene group? Now, it no longer makes sense to draw the benzene on a solid line, right? Because now carbon 1 has changed back to a tetrahedral geometry. Carbon 1 is no longer a carbocation. Now carbon 1 is a neutral carbon with 4 attached atoms. It should be tetrahedral. And we know the way to show a tetrahedron is 2 solid lines, a wedge, and a dash. So in this picture, since the oxygen is on a wedge, the benzene has to change to a dash. And in this picture, since the oxygen is on a dash, the benzene has to change to a wedge. If the oxygen attacks the flat plane from in front of the page, it pushes the benzene backwards behind the page. If the oxygen attacks the flat plane from behind the page, it pushes the benzene forward in front of the page. Now, is the mechanism finished? Probably not, because the main product still has a formal charge. Since we still have a formal charge, it looks like we need a third step, an acid-base cleanup step. Why is it called a cleanup step? Because it's going to be cleaning up the formal charge. we expect to use the positive oxygen as our strong acid. So who are we going to use as the base? Not the I-. We'll use the alcohol solvent. Use the alcohol solvent as our weak base. The electron pushing arrows go from the base, which is the electron donor, towards the proton that it's taking. And we have to redraw this hydrogen so that we can see the bond to the hydrogen. Then there's another arrow to show that the acid is losing a proton while receiving electrons. So the arrows end up on the positive formal charge. Now we're ready to draw the products from that step. This arrow tells us to draw a bond between the oxygen and the hydrogen. So now the oxygen is changed from OH to OH2. Most important, change the charge. The oxygen started neutral and lost electrons, so the oxygen should end up positive. We should be showing all of these changes in both branches of our mechanism. This arrow tells us to break the bond between the oxygen and the hydrogen and to change the charge on this oxygen from positive to neutral. Are we done with the mechanism? It looks like we probably are done because now our main products have no formal charge. We can't get rid of this formal charge or this formal charge, but our main products have no formal charge, and that's a clue that we're probably done with the problem. So the products that the professor probably cares about on this problem are these two. This problem gave us some more practice with SN1 stereochemistry. Again, we saw that SN1 reaction at a stereocenter gives us two products, one product with retention of configuration and one product with inversion of configuration. We saw how to draw the geometry for each intermediate here, including to show how the geometry of the benzene group changes in the various pictures. Remember, the key here is to know that this is an SN1 reaction. If you thought this was an SN2 reaction, you would get only one product with inversion of configuration. So make sure that you correctly identify the mechanism, because the stereochemistry for SN1 is quite different from the stereochemistry for SN2. If this had been an SN2 mechanism, we would have gotten a different answer. We also got some practice with this abbreviation ME. You should know that ME stands for a methyl group. By the way, that means that if you wanted to, you can actually draw the methyl group like this. The advantage of this approach is it makes it easier to actually number this carbon as carbon 9. And notice then that our final product would look like this. Rather than writing this as OME, we could actually use this condensed notation to actually show the methyl group. So this is also a correct way to write the answer. This is correct if you write it as Me for a methyl group, but this is also correct if you actually use the condensed notation for a methyl group. Or you could write the methyl group using bond line notation. You could also write the methyl group using bond line notation. Bond line notation maybe looks a little bit weird when there's only one carbon in the carbon chain, but this is acceptable notation. And again, an advantage of this is it lets us number the carbon. If you're going to use bond line notation, you should definitely number the carbon to avoid making a mistake. So here would be the bond line notation for this same alcohol. And here would be what the final product would look like using that bond line notation, still being careful to number this one carbon attached to the oxygen. So this would be an acceptable way to write the answer to the problem using bond line notation. This would be an acceptable way to write the answer to the problem using condensed notation for the methyl group. And this would be also an acceptable way to write the answer to the problem using the abbreviation Me for the methyl group. All three of those would be acceptable answers. You can use whichever approach you like the best. The important thing is to know that Me stands for a methyl group which is covalently bonded to this oxygen. And therefore, there's no reason to break that covalent bond in the mechanism, so that the methyl group should still be attached to the oxygen in the final products, however you decide to draw the methyl group. Make sure you draw this tetrahedral geometry correctly in the final product. tetrahedral geometry should have two solid lines, a wedge, and a dash. So notice about how around carbon 1 here we have two solid lines to carbon 6 and carbon 2, a wedge, and a dash. And here's a different pattern with two solid lines, a wedge and a dash. So in the final product, one of the substituents should end up on a wedge, and another substituent should end up on a dash. Please pause the video and try this problem. Now let's discuss. Let's start by numbering the carbons. This molecule turns out to be a solvent that doesn't participate in the reaction, so I won't bother numbering these carbons. Do you know what ET stands for? You should know that ET stands for ethyl. So this is an ethyl group. So this does have carbons, but because they're not shown separately, it's not easy to number them. So I won't number the carbons in that ethyl group. Remember, ET means an ethyl group. We don't need to look for ionic bonds. The formal charge on this sulfur is already drawn in for us. Because of this negative charge, we would expect this sulfur to act as our nucleophile. Neutral chlorine looks like a good leaving group, which would make carbon 3 our alpha carbon. And we can see that carbon 3 is a secondary alpha carbon. A secondary alpha carbon puts us in the middle row of the table. S- puts us in the middle column of the table. Here's S- in the middle column of the table. Good nucleophile weak base. Middle column and middle row of the table means the table predicts an SN2 mechanism. Make sure that you write down that mechanism. Again, don't assume the mechanisms are SN1. Use the table. This mechanism happens to be SN2. Because it's attached to the chlorine, carbon 3 has a delta positive charge, which makes carbon 3 into a reasonable electrophile. So now we can draw our mechanism. We want an arrow to show the nucleophile joining the alpha carbon. Here's the arrow to show the nucleophile joining the alpha carbon, and another arrow to show the leaving group leaving the alpha carbon. So those two things happen simultaneously in one step in an SN2 reaction. Now we draw the products. This arrow tells us to form a bond between this sulfur and carbon 3. Here's the bond that's formed between the sulfur and carbon 3. The sulfur is covalently bonded to the ethyl group in the starting materials, so the sulfur should still be covalently bonded to the ethyl group in the product. You don't break a covalent bond unless there's an arrow that tells you to break that bond. And we know this is a covalent bond because the carbon, this is a bond between a sulfur and a carbon, non-metal and a non-metal. The sulfur started negative and lost electrons, so the sulfur ends up neutral. When the sulfur attacks, our alpha carbon is still attached to its leaving group. So we use this rule. When the nucleophile attacks an atom attached to a leaving group, the nucleophile attacks from the side opposite the leaving group. Well, the chlorine is in front of carbon 3, in front of the page, so the sulfur has to attack from behind the page, so the sulfur ends up on a dash. It's crucial for getting full credit to draw the correct stereochemistry here at carbon 3. So we used this rule. This arrow tells us to break the bond between carbon 3 and the chlorine. The chlorine started neutral and gained electrons, so the chlorine ends up with a negative formal charge. Here's the product the professor would probably care about on this problem. Now, are you familiar with this molecule? It's important to realize that this molecule is a common solvent. The name of this solvent is DMSO. I discussed these common solvents, including DMSO, in the SN2 video series. So you can see from this chart that DMSO is a solvent which does not participate in SN2 and related reactions. So we treated this solvent as a spectator that wasn't participating in the reaction. Of course, you should also be familiar with these solvents, water and alcohol. You should also be familiar with the water and alcohol solvents. Water and alcohol solvents we've seen definitely can be used as nucleophiles and bases. we've seen many cases where we do use water and alcohol as nucleophiles and bases, although you should be aware we only use those when there's no better nucleophile present. For example, in this reaction, we certainly did use an alcohol as the nucleophile. But the reason we used the alcohol as the nucleophile was because there was no better nucleophile present. So this was the DMSO solvent, and it did not participate in the reaction. So the main purpose of this problem was to give us more practice with switching gears back and forth between SN1 reactions, like we did in the previous problem, and an SN2 reaction, as we did here, and to give us more practice with contrasting SN1 stereochemistry that we saw in the previous problem and SN2 stereochemistry that we saw here. In this problem, we had an SN2 reaction, so the SN2 reaction gave us inversion of configuration at the alpha carbon, from chlorine on a wedge to the sulfur on a dash. So notice it was very important to realize that this was not SN1, because if this had been an SN1 reaction, with an SN1 reaction we would expect two products, one product with inversion of configuration and another product with retention of configuration. So it's crucial, even though the problem didn't ask us to draw the mechanism, it's crucial to figure out the correct mechanism, because we'll get different products with SN1 versus SN2. With SN1 we would have gotten one product with inversion and one product with retention. But since the reaction was actually SN2, we got just the single product with inversion of configuration. Also, if you hadn't known before, you should make a note that when you see ET, that stands for for an ethyl group. We know that Me stands for a methyl group, and here we saw that ET stands for an ethyl group. Please pause the video and try this problem. Now let's work on the problem together. We can start by numbering the carbons. I've numbered all the carbons, including this one. There's no ionic bonds. We can try to identify roles. Well, there's no negative charges, so we would expect this neutral oxygen to be the nucleophile in the alcohol. Now, it looks like we have two possible leaving groups. We have the bromine here. Neutral bromine can be a leaving group, but we also have a neutral bromine here. That could also be a leaving group. So we're not quite sure which of those we're going to be using yet. And as a result, there's two possible alpha carbons. We might want to use carbon 1 as our alpha carbon, or we might want to use carbon 8 as our alpha carbon. Well, now's a good time to try to choose a mechanism. And how do we choose the mechanism? Don't assume it's an SN1 mechanism. The mechanisms on the exam will be all mixed up with each other. Use the table to determine the mechanism. Well, before we can use the table, we have to decide what types of alpha carbons we have. Carbon 8 is a primary alpha carbon. It's attached to one carbon chain. And carbon 1 is a tertiary alpha carbon because it's attached to 1, 2, 3 different carbon chains. Carbon 7, carbon 6, and carbon 2. Now we can use our table. Well, if we decide to use carbon 1 as the alpha carbon, that would put us in the bottom row of the table. And if we decide to use carbon 8 as the alpha carbon, that's a primary alpha carbon, that would put us in the top row of the table, whereas carbon 1 was tertiary. Now we're in the left column of the table, because this neutral oxygen in the alcohol is a poor nucleophile. So if we were using this row, we would say that there is no reaction. Whereas if we were using this row, we would say that the major product would come from an SN1 reaction. Well, it's quite easy to choose between those. Now we can see that this alpha carbon won't react. The table tells us that this alpha carbon will not react. Since the carbon 8 alpha carbon will not react, clearly we have to use the carbon 1 alpha carbon in an SN1 reaction. So the main challenge of this problem is to determine which alpha carbon you're going to use, and in this case the table tells you the answer. The table tells you that carbon 8 will give us no reaction, and carbon 3 will give us an SN1 reaction. Now, why is there no reaction in this cell of the table? Do you know why there's no reaction in this cell of the table? Well, that is a topic which we will discuss in a later video in this series. Now we draw the mechanism. In the first step of an SN1 reaction, the leaving group leaves. So here we've shown that the leaving group has left. Make sure you put that positive charge on carbon 1 because carbon 1 lost electrons. Also, I changed the orientation of carbon 7 to reflect that this carbocation is trigonal planar. So this is my best effort. This is my best effort to show that carbon 7 is in the same plane as carbon 6 and carbon 2. If I kept carbon 7 in this position, it definitely would not be in the same plane as carbon 6 and carbon 2. That's the best I can do in this chair picture to show that this carbon is now trigonal planar. Now we do the nucleophile electrophile step. Now I've carried out the nucleophile electrophile step. First we draw the electron pushing arrow, then we draw the product. Now, notice that when the nucleophile attacks this trigonal planar carbocation, there's two different directions it can attack from. It can attack from above or from below. If the nucleophile attacks from above, it ends up in the axial position and pushes carbon 7 back down to the equatorial position. But the nucleophile can also attack the trigonal planar carbocation from below. If it attacks from below, it ends up in the equatorial position, and carbon 7 gets pushed up to the axial position. I think this might be the first problem in this series where we've dealt with stereochemistry for a picture of chair cyclohexane. So if the stereochemistry here gave you difficulty, please pause to study how we handled representing the possible stereochemistry for the SN1 attack for chair cyclohexane. As usual in SN1 reactions, we get two possible products at a stereocenter. One with retention of the original configuration and one with inversion of the original configuration. And here's how to show that for the chair cyclohexane picture. Most important, make sure that you put the positive charge on this oxygen. And now we need another step, an acid-base cleanup. So here's the arrows for the acid-base cleanup step. We use the alcohol, another molecule of the alcohol as the weak base. Make sure that you include this positive charge to show that you've changed the charge on the oxygen. Now, based on the instructions here, probably the products that the professor cares about are these two. So these are the two that I circled as being what the professor would probably care about in their answer, but I would still encourage you to go through the entire mechanism, including all of these products, for your own understanding. So the main challenge on this problem was deciding which alpha carbon to use, carbon 1 or carbon 8, and we were able to decide that from our table. The table predicted no reaction at primary carbon 8, so instead we went with the SN1 reaction at tertiary carbon 1. Now, the other purpose of this problem was to give us some practice with SN1 stereochemistry for chair cyclohexane. So if that gave you difficulty, again, you should study how we handled the stereochemistry for the SN1 reaction in this picture of chair cyclohexane. You should know that to accurately show stereochemistry for chair cyclohexane, it has to be clear which of the substituents is axial and which is equatorial. Notice that to show that this substituent is axial, it should be pointing straight up, or in this case, straight down. The axial substituents should point straight up or straight down. And then an equatorial substituent is indicated at a slant, such as carbon 7 is equatorial here, or this oxygen is equatorial, or carbon 8 is equatorial here. So make sure that you should make sure that your answer clearly indicates which substituent is axial and which substituent is equatorial in your answer. By the way, I bet that a lot of students who would do a problem like this on an exam might just forget that they have to show more than one stereoisomer product for this problem. So make sure when you're taking the exam, make sure you remember that in many cases you're going to have to show more than one product when there are multiple stereoisomers. Don't lose credit just because you forgot to think about the different possible stereoisomer products. Remember that when we carry out SN1 at a alpha carbon where the stereochemistry matters, there are two different products. By the way, I guess this is a good opportunity to mention a technical issue. Technically, carbon 1 is not a stereocenter. Technically, carbon 1 is not a stereocenter because you'll meet the exact same path of atoms if you go one direction around the ring or if you go the other direction around the ring. So technically, carbon 1 is not a stereocenter. Nevertheless, the geometry at carbon 1 still matters because the substituents at carbon 1 can be either cis or trans to carbon 8. For example, notice that in this picture, we can see that this oxygen is cis to carbon 8 because they're both pointing up, and carbon 7 is trans to carbon 8 because 7 is pointing down and 8 is up. Whereas in this picture, carbon 7 is cis to carbon 8 because they're both pointing up, and the oxygen is trans to carbon 8 because this is pointing down and this is pointing up. So this actually gives us another situation where stereochemistry matters. In the past, I probably made it sound like stereochemistry only matters at a stereocenter. But even when an alpha carbon is not a stereocenter, the stereochemistry can still matter if there are cis and trans relationships around a ring, as we have here. So here's an updated version of the stereochemistry rule that we learned for SN1. The upshot here is that SN1 can produce two products not only when the alpha carbon is a stereocenter, but also when we have a ring with cis-trans relationships, even when the alpha carbon is not a stereocenter. I'm not going to say here that there will always be 50-50 proportion of products here, because it's possible that the other substituents could make it more difficult to attack the ring from one direction rather than the other. But we will get some products with inversion and some with retention, as we did here. So here, one more time, is a summary and contrast between what you need to know about SN1 stereochemistry and what you need to know about SN2 stereochemistry. You should have all these ideas memorized. And in this summary, I've added this new idea that the stereochemistry at the alpha carbon could matter if the alpha carbon is a stereocenter, but the alpha carbon stereochemistry might also matter because of cis-trans relationships around a ring. And that could be important either for an SN1 reaction or for an SN2 reaction. This molecule is a different molecule than this one. This product is considered a different product than this one, even though carbon 1 is not a stereocenter, because these two products have different cis-trans relationships around the ring. We've discussed in this video that if you have a simple molecule, an SN1 reaction will produce 50% inversion and 50% retention of configuration. But we've also discussed that if you have a more complicated molecule where one side of the molecule is hindered, in that case you could get unequal proportions of inversion and retention of configuration in your products. Now let's try a review quiz. Please pause the video and try to answer each of these questions before you look at the answer. What are the names of the 5 main roles in organic chemistry? I hope you answered. Here's the answer. The roles are nucleophile, electrophile, leaving group, acid, and base. Next question. How is a base similar to a nucleophile? I I hope that you actually paused and came up with an answer to this question. Here's the answer. A base is similar to a nucleophile because both a base and a nucleophile donate electrons. Next question. How is a base different from a nucleophile? Again, I really hope you're going to come up with a considered answer. Here is the answer. They're different because a nucleophile is joining the electrophile, whereas a base is taking a proton from an acid. Those are two different types of actions. Next question. Please pause the video and draw the electron-pushing arrows for an acid-base step. I hope that you actually wrote down some electron-pushing arrows. Well, we'll need an acidic atom and a basic atom, and the base is the electron donor, so the base goes at the tail of the electron-pushing arrow. But remember, the base takes a proton from the acid, so we have to assume that the acidic atom, we'll assume that the acidic atom is attached to at least one proton. So this is the key, the first arrow. This shows the base donating electrons to take a proton from the acid. We need a second arrow to show the acid receiving electrons in order to lose the proton to the base. So those would be the electron-pushing arrows for a generic acid-base step. My experience is that students have a real hard time coming up with the correct arrows for acid-base steps. So keep practicing this until it's boringly easy for you to come up with the electron-pushing arrows for an acid-base step. We've seen that most SN1 mechanisms involve an acid-base step, but the fact is most mechanisms in your Ochem class will involve acid-base steps. So it's crucial to be familiar with the electron-pushing arrows for an acid-base step. Remember, you definitely should not draw an arrow like this. Don't show the base attacking the acid directly. The base does not attack the acidic atom directly. It takes a proton from the acid. And of course, don't draw an arrow like this. We're not trying to show that the proton is moving towards the base. We're trying to show that the electrons are moving away from the base. All of this material on the screen is crucial for your success in organic chemistry. So I hope that all these questions were boringly easy for you. If not, you need to keep practicing these ideas until they are boringly easy. That's the only way to succeed in organic chemistry. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.